So yesterday I was visiting Scilab at CMU, Carnegie Mellon University. They have a really great security research center. And today I am at another great security research center. So today I'm going to talk about measuring attack surfaces of enterprise software systems. How many of you have heard about attack surface measurement? Okay, just one. So the goal of this talk is to increase this number from 1 to 20, around 20, right? So you're here. So we started working on this project because we had some interesting, challenging questions almost 2 years ago. The first question was, how can we quantify a software system's security? And I think it's a difficult question, right? And another related question was, how can we determine that one release of a software system is more secure than an earlier version? How do you know that? So, it's difficult, yeah. That's why we decided to work on this. And let me start with a challenge related to these questions. I think first of all we need to accept the fact that application security is difficult to achieve. So because when you talk about security, you can talk about application security, network security, operating system security, virtualization, other things. But in general, application security is difficult to achieve because of following reasons. The first reason is applications are really complex. So have you ever seen an enterprise application solution which has code around 300 million lines? So these kind of applications exist, and imagine also that the customers are buying these applications and also customizing, adding more code, and also deploy different versions with different customizations in their platform, application computing platform. So another reason is applications are complex. Another reason is complex architectural structure. So we are seeing more and more emerging application structures like service-oriented architecture, software as a service, and applications, Web2O applications where we have more, let's say, business logic on the client side in compared to the traditional web applications, and also new application platforms like mobile devices, for example. So there we don't have too much complexity, but we have challenging environments where the applications are running. So the second category of reasons is around what's happening in the area of attacks and security. So security boundaries have dissolved actually. If you look at today's applications, the applications are open to the public. You can deploy an application as a web application, and everybody can see this application. Of course, you have to have necessary credentials to work on these applications, but the attackers may also somehow use web to enter these applications, access these applications. So attacks are increasing. Not only attacks, but also attack types are increasing. So an attack, let's say integer overflow or cross-site request forgery, for example, which have not been known 5 years ago, 10 years ago, they are now there. So the applications written 5 years, 10 years ago, so they didn't know that this kind of attacks would happen, and they were not prepared to defend themselves against this kind of attacks. And another interesting thing is that attackers are focusing more on applications. So they love applications. So and of course there are more potential attackers and more sophisticated tools. This means that the attackers don't really need to have a lot of knowledge to conduct, let's say, attacks which might have huge damage potential. So what is the industry doing? Industry has been doing lots of things around code quality. So we are trying to improve the code quality, all right? So what does this mean actually? So I think the best thing what you can do is with today's standards, you can try to integrate, you should actually integrate the security into software development lifecycle, right? So you have requirements phase, you have design phase, let's say you have implementation, quality validation, and then you deploy the application, the customer environment, for example. So there are lots of things what you can do in each of these phases. I'm not going to talk in detail about these things, but for example, during the requirements phase, of course, you should understand the requirements, the security requirements driven from your company's policies and also some regulations, for example. And in the design phase, you should create some application threat modeling, and you should perform security risk assessment and follow some security design principles, because design is extremely important because implementation will be based on design. And then you should create some security test cases. Actually, you should also look at the abuse cases, right? So you create abuse cases. And during implementation, hopefully you have really good secure programming guidelines, and the programmers or developers are trained in using these guidelines. And then they do programming based on these guidelines, and then you still run some automated security test cases, and then, which is very important, you perform some security code review, which might be automated and or a combination of automated code review plus manual code review, because today's automated techniques, static analysis techniques, are not sufficient to find all kind of vulnerabilities. You really need to do a manual code review. So, and then in the quality validation phase, then you do additional things. If there are some security bugs remain, then hopefully they will be found during the quality validation. Again, you do other kind of tests, penetration tests, for example, and then hopefully your software is secure, and then your software is probably certified, saying, this software is secure, it looks secure. And during the production phase, this is very important. If you configure your software in a wrong way, so a lot of things can happen. Most of the, not most of the, but an important portion of the security problems arise, around misconfiguration. Okay, so all of these efforts are trying to reduce the number of design and coding errors, right? So we are trying to find all possible design and coding errors, and we are trying to remove them before we deploy the applications in let's say, customer environments. So the question is now, is code quality improvement enough? So the answer is this graphic, right? So look at the number of vulnerabilities from 2000 to 2007. So you see, the number of vulnerabilities, reported vulnerabilities, has been increasing. So of course, if you do all of these things I explained in the software development lifecycle, your application is probably, let's say, secure enough, might be secure, secure. But how many of the developers, are really trained in security, in particular the developers writing web applications? How many of them have secure object-oriented design, knowledge, or secure system design knowledge, etc.? So it looks, code quality improvement, if you do it really in a good way, this is excellent. All of the big software vendors are doing these things. But it looks it is not really enough, right? So what we can say is our code is only perfect by today's standards. But new vulnerabilities are constantly evolving, right? So the fact is, shipping, vulnerability-free software is hard because it is hard to detect and remove known vulnerabilities, and we don't know about future vulnerabilities. And we have to accept the fact that software will ship always with known and future vulnerabilities. So the argument is here, is following. Software vendors need to change their outlook from saying my code is very good quality to my code is the best it can be with today's knowledge. It likely still has security defects. Okay. So what should we do? We should try to minimize the risk associated with exploitation of vulnerabilities, in particular exploitation of future vulnerabilities. How do we do this? So we should try to reduce the attack surface. Because if you have a smaller attack surface, you have a less risk associated with future vulnerabilities, right? And we could make the exploitation harder, and we can also lower the damage potential. So the ideal case is, is to have a, great code quality efforts and also attack surface measurement. And if our application is in the green, let's say, phase here, this means that we have a really low security risk associated with the future vulnerabilities, because we did everything we could do during the code quality efforts. And plus, we also try to measure attack surface and reduce it. Then we are probably more protected than we were protected, in the past. So the fact is, if you cannot measure something, it's not only valid for software, right? If you cannot measure something, you can't improve it. So we really need to have some kind of measurement and metrics. And metrics in the area of security is very difficult. I mean, it's a really challenging task, right? That's why the research questions I was asking at the beginning, they are really difficult to answer. But I think with the efforts around attack surface measurement, so we came, a few steps closer to the answer. And so we have to do, more and more research in this area, I think. So how do we do this? So in the next 30 minutes, I'm going to present you the abstract attack surface measurement method, and I will talk about instantiation for Java and a case study we did at SAP Research, and also implementation. So I'm trying to give you a kind of intuitive feel, how you can measure the attack surface and what it means in a concrete application. So if you are interested in more details, because we have lots of formal techniques which are explained in the papers, so just contact me and then you can look at the papers. So, okay, what is the intuition behind the attack surface? So consider a system. A system always lives in an environment, right? So we have the system surface, and the system interacts with its environment through the system surface. So this is a kind of abstraction. So a system's attack surface is the ways in which an attacker can enter the system and potentially cause damage. So the question is now, what are these ways? Of course, methods, channels, right? The attacker needs to connect, access the method through a channel. This could be a kind of TCP socket, for example. And data, untrusted data items, right? The system may send some data to its environment or read some data from the environment. If you look at how the attacks happen, SQL injection, cross-site scripting, other kind of things. So I think all kinds of attacks, happen around this principle. They either use, channel and then access a method and then send the data, or your application reads the data from a file, but the file already includes some malicious code or data, etc. So this is how it works actually. So, okay, but the important thing here is, you have resources in your software, but not all resources are part of the attack surface, right? So I think the naive way will be to say, I count the number of bugs I find and then reduce them and say, okay, my software is now more secure. We really need to look at the code. We really need to look at the sources, because if the software causes security problems, we really need to understand our software and then see what kind of resources are contributing, how much. What is the damage potential associated with each individual source? So, so the interesting resources are the resources that the attacker can use to send data into or receive data from the system, and that's why we need to identify the entry and exit points. These are the methods and other things like channels and data items, etc., so that we know, which resources are more relevant than others. Another thing is, not all resources contribute equally to the attack surface. Right? If you have two methods, the first method runs with the root privilege, and another method runs without root privilege. And if the attacker somehow finds the chance to attack the first method, he can probably cause more damage than he can do when he will attack the second method. So that's why we need to compute the damage potential effort ratio for each resource. And the higher the damage potential, the higher the contribution, as I said at the beginning, and the higher the effort, the lower the contribution. So these two aspects are very important, right? Which resources are important and how much is their contribution. Okay, so let me now introduce the abstract attack surface measurement method. So what we do is we first identify the set of the methods, entry, exit points, channels, and untrusted data items. So M, C, and D representing these things respectively. And we estimate each relevant source's damage potential effort ratio. And then compute the attack surface measurement. So it is the sum of, if I know the damage potential effort ratio for each individual method, then I have a number for all of my methods. If I know the damage potential effort ratio of my channels used in my application, then I know the contribution of the channels to the attack surface of my application, and the same thing applies for the data items. So this is the abstract methodology. And let's now see what we did. So this methodology has been actually refined, developed and refined at Carnegie Mellon University. So the original idea is actually coming from a paper published in 1975 from Zals and Schroeder. So they have been talking about secure design principles. And Michael Howard from Microsoft developed a kind of intuitive approach, pragmatic approach about attack surface measurement, and Carnegie Mellon researchers, Janet Bing and Pratish Manatata, formalized the methodology and also validated it in different systems. So we wanted to understand what this methodology means in the context of enterprise applications. Because the previous work was validated in the context of C, C++ based code. So we wanted to first understand what does it mean, for SAP applications, or middleware technologies written in Java, and how can we demonstrate that the method scales to enterprise software? And we also wanted to investigate the possibility of integration with SAP's software development lifecycle. So this was the goal of the collaboration, and we took a middleware component, which we call now here service. So what we did is actually we developed a methodology. It's a kind of instantiation of this abstract methodology for Java, because if you want to apply this abstract method in different languages and environments, you have to really adjust it a little bit, tune it to the language and also its application environment. And so we started this collaboration last year, and I mentioned that there are three types of resources: methods, channels, and untrusted data items. So in our case study, we focus on the method dimension because in the application we choose, there was only one communication channel. There was only one TCP socket, and the service we were analyzing didn't use persistent data. That's why we focus on the method dimension. So for this, we had to identify the entry points and exit points of the service, of the application, of the code, and also estimate the damage potential effort ratio using the method's sources of inputs. So I mentioned, entry point and exit point. So what's an entry point? What's an exit point? So an entry point is a method that receives data items from the system environment. An exit point is a method that sends data items to the environment. So how did we identify the entry points in Java? So we look actually at the different interfaces used in the application. So M is a method in as a system's public interface and receives data items as input. So we look at at which kind of methods we should look. So we look at the methods in the public interfaces and which receive data as input, and M invokes a method in the interface of a system, right? Because if you consider a method actually, so it may also call another method in another system. And plus, it may also call some system libraries, Java I/O library methods, for example. This might be, for example, read methods in the Java I/O data input stream. So we look actually what the method is doing if the method is an entry point. If the method is an exit point, we look at the methods, of course, method sending data into, as a result. So, and methods, invoking a method in the interface of a system S, and receives data items as input, and also methods invoking interfaces in the Java IO library. But in this case, the method is using a write method to write something, because the method wants to store something in a store. Okay, so how do we do this? Actually, we first we take the code, we generate a call graph of the code, and we identify the interface methods of the service, and also interface methods of other systems, because you shouldn't only look at your system, you should also look at the interface methods of other systems, because your system's methods are communicating with the methods of other systems, right? And plus also some Java IO library methods. And in our case, the service we analyzed had 26 other system interfaces and 126 methods, internal methods. And so remember, we have to compute two things, right? We have to compute the damage potential ratio, the damage potential of each individual method, plus the effort, right? So in this case, in this application, we had to look at the sources of input instead of privileges. In case of C-based applications, when you do the attack surface analysis in C-based applications, you look at the method's privilege. But in our case, privilege was not useful, because the entire service was running with the privilege of the application server on which the service was running. So we didn't have fine-grained, privileges. That's why we had to think about, okay, what should we consider here when we measure the attack surface of the application? So we looked at the sources of input. What are the sources of input? Source of input includes things like input parameter, right? Because a method had some input parameter, receives some data, or returns some data maybe, and also calls other systems, and also communicate with the data stores. So for example, if you look at the SQL injection and cross-site scripting, what happens there is a method receives data items from an attacker as an input parameter in case of these attack types. So then it makes sense to consider sources of input in order to compute the damage potential. The same thing applies to another attacks, like a method receives data items from the data store in case of file existing check attacks, right? The attacker wants to know, oh, does this exist, or not? So in this case, the method needs to invoke or receive data items from the data store. So in order to compute the effort, we look at the access rights related to the methods. So for this purpose, since we have two types of interfaces, internal, public and internal interfaces, like public interfaces which can be called by other systems and from the environment, and internal interfaces which can only be called by the application itself. And that's why we look at two types of access rights, public and internal access rights. So so the interesting thing is now, okay, let's say we identified these things, and how do we now compute the damage potential? So we somehow need to assign some numbers. For example, is input parameter more important than data store and other system? Because we somehow need to give some weights, to these kind of inputs of resources, which are very important to compute the damage potential. So what we did actually, we looked at the threat modeling, which has been done in the context of the SAP service, and we tried to understand what kind of attacks are possible in this kind of applications. And we found that parameters, for example, are extremely important. As I said, for example, SQL injection, cross-site scripting are misusing the input parameter of a method. That's why we gave some weights. But I'm not going to talk about why we really gave 5, 3, and 1, or not something else. So there is a sensitivity analysis technique which has been developed at CMU, and we used their methodology and experiments to give these weights.
But I have one question.
Sure.
Which is the following. So okay, suppose I consider a method. Okay, so really the risk depends on what the method does, because if the method is a method accessing a password file, then the risk of giving a bad parameter, like in the case of SQL injection, would be very high, not because of the parameter itself, because of what the method is going to access.
Right. So the method
If
has, in this case, had high potential, damage
exactly, but this is not implicitly given. It's just because the method will access certain very sensitive resources.
Yes.
If another method doesn't access sensitive resource, then it can be attacked, but it's not really a serious
Exactly. That's
problem.
why we have
So
to know.
how do you tie those numbers to the actual actions that the method will do? You see what I'm saying?
Yes, yes.
Okay.
Actually, I skipped that part, but you somehow have to have an understanding what your code is doing. That's why you really need to look at your code. So, and since you wouldn't probably have hundred thousands of methods, accepting user ID and password as input, so you have certain points where you do some authentication checks and authorization checks. You have to know these methods, and of course you will assign higher values to these methods. So we do kind of annotation of the code, and then generate the call graph.
Yeah, but again, I don't know whether starting from the code is a good idea. Because in my view, I would start from the resources I want to protect. So say, I want to protect the password file, okay? And then after that, I need to look all the code which accesses. While you are suggesting to do the opposite, I look at the code by itself. That may be much more expensive to do. But,
yeah, I mean,
no.
otherwise, how can you understand the semantic, of the code? You really need to distinguish between the methods which might have higher contribution than the others.
Exactly. Once you know which are the sensitive resources,
Right.
which I mean files or other resources, then you have to syntactically see which are the methods which access the particular resource.
Okay.
And once you have done that, then you can look at those methods and really see what they do.
I see. But you may have,
Yeah.
if you have this knowledge,
Yeah.
if you really have this knowledge, which method is accessing which,
Yeah.
sensitive data,
Yeah.
so you could definitely, inject this knowledge into the analysis. So in our case, in this case study, we had some assumptions, of course, and constraints, etc. So we thought that this is the best working approach in the case of this test, case study, because it always depends on how the application is implemented. Is the authentication, authorization checks done within the code, or is it somehow separated? Do you really know if your code basis is 50,000 lines of code, for example? Do you really know where these kind of checks are done or not? So it depends really on the application, and your approach might also work.
I'm talking exactly. My approach really, no, it's not really my approach, but in order to compute those values, it would be more sense to tie that to the actual resources accessed by method or applications.
Yeah, I agree.
But,
Yeah.
okay, but that's all. Okay.
Lawrence. Okay. So we implemented a tool because the goal of the research is not just to understand how attack surface measurement works. We want to give something to developers which they can use when they add new code, or when they remove code, or when they add patch. There are different use cases how attack surface measurement tools can be used in application development environments. So we wanted to develop a tool with which we can do this analysis, and it's a kind of Eclipse plug-in. And basically, what the developer needs to do is he says, okay, I have 50,000 lines of code, but I would like to do the analysis on this part of the code. He can scope the code and then just click the attack surface measurements button, and then he gets the result computed. Of course, in order to do that, you have to feed the tool with some configuration data. In this case, you have to list you have to feed the tool with the list of Java IO libraries, and feed the tool with the list of other systems interface methods, right? And also this numeric value assignment we have been talking, right? Because that input parameter is more important than the data store, for example. So we did an experiment with three versions of the service, and then we found that the latest version of the service has slightly bigger attack surface. But the good thing was here that if you look at the service 3 and compare it to service 2 and 1 earlier versions, what the developers did actually, they defined 4 interfaces as internal interfaces, which cannot be accessed by outside, right? So I think it was a very good design decision. The attack surface would have been much higher if they had these 4 services as public services. So the measurement results of 3 versions conform to the expectation. And what you can also do with the tool is you don't want to see boring text, showing you the attack surfaces at different layers, class package level, method level, etc. So you can really see for example, which class of the entire application has the highest contribution. Or you can see, for example, show me the top 10 contribution, because if you have let's say million lines of code, so you don't have the time to analyze the entire code. You want to really see so where are the problems, right? So and you can see the top 10 contribution, and then when you do refactorization, for example, or when you try to improve your code, when you want to come up with a new release of your code, and you can really focus on this part of the code. And you can also look at attack surface measurement at the method level. So you can see, for example, so what is the contribution of the data store, what is the contribution of the parameter, input parameter, and other systems. So potential user scenario. So the question is now, okay, let's say we were able to understand the abstract method. We instantiated it for Java and did an experiment in a Java-based enterprise application. So how can we use this tool, right? The tool can be used during the design and implementation to measure and reduce attack surface. The developers of software vendors can use this tool. Of course, the customers, because customers are customizing the code. And you can also use the tool during the testing phase, in particular during the code inspection. Because imagine you have now 3 million lines of code and you want to do code inspection. Usually the software vendors are doing code inspection in order to catch the performance-related, security-related implementation bugs and defects. So, but they don't have the time to do the code inspection on the entire code. That's why they select a portion of the code. What you can do is actually you can run the code, the tool on the entire 50 million lines of code, and then see where you should start with the code inspection, because probably this part, the top 10 contribution of your software, has probably will probably have more security issues in the future because you have more methods dealing with input parameters and communicating with outside, etc., or have some sensitive methods, for example, checking authentication, authorization, etc. So you can also use the tool in the deployment phase. So we don't do it with the current tool, but I can imagine that for example, each time customer system administrator configures the application and changes the configuration, he can see, okay, now with this configuration I have the optimal or the minimal attack surface, right? So, during the maintenance, if you add some patches, for example, you can also see, does this patch increase the attack surface? Because if you found a security bug and you add a patch to your software, it will be great if the patch wouldn't increase attack surface. It probably solves the problem, removes the bug somehow, right? But it may open some other channels. So that's why the ideal case is, adding patches in a way that the attack surface doesn't increase. So what we believe is, we believe that the complete risk management requires the combination of code quality and attack surface reduction. I'm happy that we started with the collaboration with CMU, and then we are now, we have a now better understanding what attack surface measurement will mean in the context of enterprise applications. And currently, we are exploring the use of attack surface measurement in code inspection, as I mentioned. I think this will be a great, let's say, tool in order to do the code inspection in an efficient way. And so we did analysis in Java-based applications. We plan to extend the work to JavaScript and ABAP is SAP's proprietary, it's a database-oriented language, and most of the application or logic has been written in ABAP. And we also need to find the kind of range, because so you have seen these graphics and numbers. So if you look at this tool, it is possible to give a threshold, because with each threshold you will see different numbers. So the question is now, what is the threshold? You won't be able to probably find a number like if it is under 50, then you have a less attack surface, or it's acceptable. You will probably need to come up with some ranges, right? This is the kind of optimal acceptable attack surface. And we also need to prepare kind of attack surface reduction guideline, because the tool is measuring the attack surface. Now the question is, once you have measured the attack surface and it doesn't have an acceptable range, how do you reduce it? Because reduction means you have to turn off some services which are not required, right? So because you may not guarantee this always, because if you talk about applications having millions lines of code, so we may have some services and methods, we have implemented them, but let's say 80% of the customers don't really use them. Might be the case. So the question is now, shall we turn on these services when we deploy the applications in all customer environments, or shall we just turn on them or turn off them if certain customers do not require it? So we also need to do further research. Like it's really interesting to do kind of research in order to understand, can we do attack surface analysis in the absence of source code? Because as Elisa mentioned, so it might be a little bit expensive to do a measurement. So if each time if you need to look at the code and annotate, etc. So I would like to thank our collaborators from CMU. Patrish Manatada is a PhD student. He actually recently defended his PhD, and Janet Wing, advisor. And I also had an intern working with me at SAP Research. He is now back to Colorado State University. He still works for us, and he helped us implementing the visualization tool, and also several SAP Research and product teams. Their help was really good. Thank you very much. So, any questions?
I would like to thank Eugene for the very interesting talk. So, if there are questions, okay, go ahead. Okay, let's do this. Okay, go ahead. You have to talk into the.
Okay. During the measurement of the potential risk, you give weight for different input resources.
Right.
But at the beginning of the talk, you said it's hard to measure the risk because the situation and the environment will change. But how do you validate the number you give to different kind of?
So I mentioned that we looked at the threat modeling which has been done for the service. This means when you do the threat modeling, you see, okay, these 5 types of threats might happen, or had happened in the past, and you look then at how these kind of vulnerabilities, how these threats really work. And if you have, for example, if you had more SQL injection problems, or if you think that you will have more SQL injection problems in this type of applications, then you see how SQL injection really works. And if SQL injection uses input parameter or misuses input parameter of a method, then you give a higher rate to this certain input parameter of the method. So somehow you need to understand the challenges, threats around a service. Otherwise, you really need to you have to feed the tool with some weights which make sense for individual applications. So there won't be any attack surface measurement tool or approach which will work for all kind of applications. So otherwise, we have something like this, automated static code analysis tools. You can buy them, or you can hire companies to do this analysis. They don't find everything. They don't find everything because they don't really understand the semantic of the code. So, or at least most of them don't understand. So you have to understand the threats around the service, and then give the weights based on the possible threats and how these threats happen.
So you kind of predict the possible kinds of attacks.
Right. You actually, either you predict it, okay, or you look at, for example, earlier versions, deployments of earlier versions in customer environments, and or other kind of applications or vulnerabilities happen in similar application types. And if you, for example, look at different type of applications where SQL injection happens, you have a kind of understanding how this attack really works and in which kind of applications. So you have to predict it, yeah.
Yes, I have a specific question about the data you introduced at the beginning. Because you talked about method,
Channel,
channel,
untrusted data items.
and untrusted data. How do you define them exactly? Are data which are, let me say, input to the application directly by the caller of the application through parameters of a method, or are other kind of data, for example, data contained in a kind of data store,
So I think,
possibly managed by an external component?
yeah. So I think it is not that difficult to find the channels and data items, because if your application runs on an application server, and you can see, okay, through which sockets the user's request actually accessing this application, and in which databases, in which files this application is writing or reading from. And in case of methods, we use this call graph generators. So because in a very complex application, because I mentioned here only the direct entry and exit points, direct methods. You may also have indirect entry and exit points. So we didn't look at these indirect entry and exit points, but you would extend the call graph generators, to find these things. So the answer is, in particular for the methods, you have a call graph generator showing you, what are the entry points and what other methods these entry points are calling. What are the parameters, and are they writing into a database, or calling the public interfaces of other systems, or calling the methods of the Java library, for example, IO library. Yeah. So if you are interested, we can talk about how this call graph generation really works.
Yeah,
so we have.
Because my let me say, my point and my impression is that what we lack really is a good confinement of the problems. Okay, and so one of the most difficult problems to tackle are, let me say, vulnerabilities or attacks which might arise by, let me say, not directly but indirectly.
Yes.
Some data which was modified by someone else, or some data which was modified by the application under consideration, but through a number of different steps.
I understand.
And this really tends to make the tree of paths that you must follow
Right. So
unmanageable.
I think it depends on the quality of the attack surface measurement method. What we are saying here is, okay, you have excellent code guideline principles. You do everything what you can do in different phases, and measure also attack surface as much as you can, and then reduce it. So you just reduce the risk, but you don't, bring the risk to zero, right? You just reduce the risk. And I agree that in a complex application environment, it might not be enough to just look at the application, right? Because, or service, in this case, we looked at one service, but if you look at this middleware system we have, this is one of many services, right? So you should actually look at the entire environment and try to reduce the attack surfaces, but you may still not find these indirect things, because I can do whatever I can do for a service, but if some other service is writing data or reading data from a file or from a system where the data integrity is actually, has been, let's say, modified. The integrity has been broken, let's say. So, and I'm reading the data from this service, but as the service requesting service, I cannot know, whether the data is integrity is okay or not. So, in case of service and applications calling many other applications and services, attack surface measurement might be challenging.
Yeah, exactly. So I have some comments. So first of all, when you mentioned that in the conclusion, you really want to deal with, really try to reduce this attack surface.
Right.
And that seems to me quite challenging to do, because at the end you needed to shut down some communication channel. But why were they there in the first place? I mean,
Yeah,
if they were there, probably there were some requirements
exactly.
for them.
This is a very good question. The question is, when I talked to some people about this approach, the response was, we need all of this functionality. So, yes, if you need it, if you need a functionality, there are many different ways how we can implement this functionality.
But
First
then
of all, how we
what
can design this functionality. Imagine, for example, you want to provide a help functionality in an application. Most applications, you have help functionality. So you can implement it in different ways. What you can do, okay, I have this help functionality, and can say the users are able to search based on the keywords and find some help information. And if you do input validation, for example, so you probably reduce the risk associated with some vulnerabilities. But if you get rid of the help functionality as a search function and implement the help functionality as a navigation, for example, service, you wouldn't probably have SQL injection problems, because the users wouldn't have the possibility to enter code, right? Into the help form, keyword form. So what I'm saying is, I think the ideal thing is, when we do design, software design, we should really review the design from the attack surface point of view. Not only, okay, we need to have these 3 tiers, we need to put the application server behind the web server, we have more tiers, more boundaries, etc., etc. We should do that. But we should go, we should have a kind of finer design review, where we should say, okay, you know what, if you need this functionality, and what are the ways of implementing it, and what is the best way of implementing it from the attack surface point of view. And we should do the second thing at the implementation layer, etc., etc. So, but then you can look at the implementation again and say, okay, we did everything we could do. Now we have a kind of good attack surface, it's acceptable. But now the applications are evolving, right? They are changing. The specifications and assumptions are changing. When you do, for example, patches, or when you do refactorization, you should still get this knowledge. Where should I start? Because it's not 100 lines of code. It is million lines of code. You should have some kind of intuitive feel. Okay, we will start refactorization here, and probably provide the same functionality in a way that this part of the code has a less attack surface contribution. So I'm not saying that you should turn off the services and etc. But definitely it's a good idea to know. You know what? If one service was in this top 10, for example, area, and 80% of the customers don't use really this service, let's turn this off. This is how
that's a good point. But in other cases, if you change so that you reduce the number of those channels, you may have an impact on the performance and usability by the user point of view.
You will have always kind of trade-offs. The trade-off will be,
trade-off.
I need this functionality, but it has a big contribution to the attack surface. So you should try to somehow reduce, if you can redesign or re-implement it, etc. But if you cannot do that, at least even if you cannot reduce it, at least that this part of your code in these million lines of code has the has the highest risk.
So you can.
And the question is now, without measuring it, you don't know it.
That's
because with today's techniques, what you are trying to do is, you are trying to get rid of all existing implementation bugs, security defects. But you don't know And when you do that, you have some kind of assumptions. But you write an application, this application, lives 30 years, 40 years. If you look at, for example, SAP's applications, we had this R1, R3, R2, R3. So we have still lots of customers using code which have been developed in 80s, right? So we still maintain, let's say, this code, or customers are maintaining this code. So I think this will be a good complementary approach in addition to the code guidelines.
I think that there are a lot of issues to be discussed.
Oh, yeah. Yeah.
Okay, thanks. And I think
Thank you very much.
Oh.
Thanks.